Okay, good morning. So before I start with today's lecture, I just want to remind you that 27th is your test. It's SPM, solid state physics. And the chapters would be from your book. It's chapter number 1 and chapter number 3. Okay. This is not going to be MCQ. This is going to be a proctored examination of 50 minutes. I hope you know the time of the exam. On Friday, it is from 4:30 to 5:30. So what I want you to do is ensure that you are sitting in a place where there is power. In case there is a power issue at your place, please move to some location, go to some neighbor's house where there is a backup power. It's after all a laptop that you need to carry. Your phone and your laptop, carry it, go and sit. No makeup is going to be given because it's just 6 of you. For 6 of you, we cannot keep making question papers again and again. So again, I repeat, no makeup is going to be given. Okay, this is a decision that all of us have taken. And next thing is, what would be the type of questions? Okay, the questions, like for example, you will be required to know indexing of planes, indexing of directions. Like I may give a figure or I may give a description. I want you to do the indexing. This is, I just briefly touched here, but then you have done this in SPM. So one should not be wasting time teaching that again. So I just touched upon it. Then, of course, the concept of brevis lattice. You could be asked any of the brevis lattices to describe or draw or whatever. Okay, brevis lattice. And then reciprocal lattice. Then what else can be asked? Anyone? What else can be asked? Then what we are going to do today, that also can be asked. Okay, so this is going to be analysis of X-ray diffraction patterns from crystals. And see here, when I'm talking of different types of crystals, like for example, if I'm talking of simple cubic, BCC, FCC, etc., you must know where the atoms are placed. And similarly, you should know how you write your A, B, C vectors. And similarly, you should know how to write your A star, B star, C star. Okay, all these things will be required because I really don't know whether we should call them problems. There will be some theory and there will be some problems. Problems in the sense you may not require a calculator to do it, but a concept based. Any doubts? Any doubts?
No, ma'am.
No. Okay. So let's start off with today's part of the syllabus. So we are talking of analysis of X-ray diffraction patterns for crystals. Okay. So what does this mean? Okay. So the last few classes I've been talking about, actually this chapter itself is talking about X-ray diffraction. We talked about Lewis condition, we talked about Bragg's law, and the equivalence of both these also we have discussed. So in an actual situation, what exactly happens in a lab? There are different types of X-ray diffraction methods. We will just talk about one, and that's called the powder method. In a powder method, what happens is you take a crystalline material, make it into a powder, and then put the powder in some base, okay, put the powder and allow it to hit the X-ray. Allow it to hit the X-ray. So you should remember that, there will be a diffraction maxima that you're getting corresponding to different crystallites within the material. Please remember, within this itself, now this is made up of different crystallites, and within each of these crystallites, there will be planes of various orientations, and all the planes which are going to satisfy the condition 2D sine theta equal to m lambda will give rise to diffraction. And another thing is, this is here what happens is, this is the X-ray is coming like this. The incident angle is here. So here what happens is you will be rotating the sample. This is your sample. You will be rotating the sample. By rotating the sample, what happens is you are changing the angle between the X-ray and the material. Okay, you're doing it so that different planes in the material will be exposed to the X-ray and will be able to satisfy that condition 2d sine theta equal to m lambda. And please remember, if I take a cell, let's say I'm talking about a cell like this, okay? And if I'm talking about a plane here, this plane is going to have, if I take parallel planes like that, d value is going to be different. If I take this and this as a plane, here d value is going to be different. If I take this and the one behind as plane, d value is going to be different. So d is actually the shortest distance between parallel planes. A family of planes, the shortest distance is d. So that means what you will see is for different families of planes, this equation will be satisfied for different values of theta. Because after all, in this equation, lambda is the wavelength of the X-ray you're using. M is going to be equal to 1. So if D is going to be different for different planes, theta also will be different. Okay, so what happens is when you rotate the sample like this, different crystallites and different planes will get exposed to the X-ray, and therefore you will have constructive interference, or you will have a diffraction corresponding to different angles coming from different planes. So what is normally done is there will be a sheet of paper which you will be, I'm sure you people must have seen your grandfather's or your father's ECG. Okay, it's actually a strip of paper on which you see the pattern. Similarly, here also what happens is it will be a strip of paper on which, you're going to see the intensity of the reflected. The y-axis is the intensity of the reflected X-ray. And you're going to see that these are the background. This is the background. But suddenly in between, you will find, these are called peaks. You will find peaks. And these peaks correspond to different values of 2 theta. Angle will be taken as 2 theta. Like for example, if this is 82, then theta is 82 means, 2 theta is 82 means theta is 41. So at theta equal to 41 degrees, I am seeing a peak. Similarly here, at theta equal to some 34, I am seeing a peak. Similarly, for different values of thetas, you're going to see peaks. Okay? So this is called a diffraction pattern. By studying this pattern, you can actually understand what was your crystal, what is ABC for the crystal, is the crystal simple cubic, is it BCC, is it orthorhombic? All this information can be obtained by just this pattern. Just like a doctor can look at the ECG and then say what is the condition of the heart of the patient or what is wrong with the patient, the doctor would be saying. It's a signature. ECG is a signature. Similarly, here, the X-ray diffraction pattern is a signature for the given crystal. Is this clear? Please answer.
Yes, ma'am.
Yeah. So you can see that what I have given here is the X-ray pattern, XRD pattern. XRD means X-ray diffraction. XRD pattern for a BCC metal. Okay. And you must notice that I have written some numbers here. What is this? This 100 in this bracket means we are writing the HKL for the planes from which this reflection happened. It has happened from the family of planes 110. This peak came from the family of planes 200. This came from the family 211. So this is called indexing the peaks. So there are softwares which you will use for indexing the peaks. And after indexing the peaks, you will be able to actually say something about what is the crystal. Okay. So before we get into it, let us look at the physics of it. Okay. So first you consider a primitive cell. You know what's a primitive cell? A primitive cell is one in which there is only one lattice point. And attached to that lattice point, you may have 1 atom, 2 atom, 3 atoms, the basis. Okay. So now we will consider a primitive cell which is having as basis n identical atoms. The basis of this primitive cell is going to be, each lattice point is going to be associated with n identical atoms. And the positions of these atoms are given as R1, R2, R3, Rn. Okay? And you will get a diffraction peak, as I mentioned, only when there is a constructive interference from X-rays which are getting reflected from the same families of planes. Let's say I have planes like this. So from the different planes, there will be reflection. So if there is a constructive interference corresponding to theta, that is when you will get a intense diffraction peak. Okay. And you also studied in the beginning of the chapter, that when there is a reflection from a given plane, then the change in wave vector is k minus k prime equal to g, where g is the reciprocal lattice corresponding to that family of plane. Okay. And whenever you're talking of interference in optics you've studied, you will be talking of what is called the path difference. So let us consider the rays reflected from some Ri position and atom at Rj position. Okay. Then what will be the path difference? Path difference will be G dot Ri minus Rj. A path difference also means a phase difference. The phase difference will be an exponential of Ig dot Ri minus Rj, or exponential of I into the path difference. This is all from optics. Okay. Now what you do is, let us say your primitive cell is having n number of cells. Then what happens is, you have to consider all these n atoms and talk about the amplitude of the X-rays reflected by the cell. Your cell has got n atoms. You can talk about the amplitude of the X-rays reflected by the n cell belonging to this primitive cell. And you will find that the expression for the amplitude, the equation for the amplitude, is going to contain this expression, summation of exponential Ig dot Rj. And this exponential Ig dot Rj, I told you, is the path difference, corresponds to the path difference. So the amplitude of X-ray reflected from a given primitive cell containing n atoms is going to be containing this term, summation exponential Ig dot Rj. So I said it is going to contain this term. So now what will be the exact term? The exact term is therefore going to be Sg equal to summation a factor Fj into this exponential Ig dot Rj. This is all mathematics, okay? So let's just go quickly. And this Sg is called the structure factor. The amplitude of the X-ray scattered by a primitive cell is going to be represented by the equation Sg equal to summation a factor Fj into exponential Ig dot Rj. You're going to do summation for all the n atoms present inside that primitive cell. And Sg is called the structure factor. And what is this Fj? Fj is called the atomic form factor. Atomic form factor. And this atomic form factor will depend on what is your atom. It is going to depend on the structure of the atom. Like, for example, how many electrons are there? What is the electronic configuration? And things like that will decide what is the atomic form factor. Okay, now we know that we have started with saying that our cell, our primitive cell, is going to have n identical atoms. N identical atoms. So since Fj is attributed to the property of the atom, this Fj will be same for each of the n atoms. You have n atoms, all identical, therefore Fj will be the same. So let's call Fj as some F. So let's take it out of the summation. Therefore, you say that the reflection from all the atoms of your primitive cell is going to be given by the structure factor F into summation exponential Ig dot Rj. Okay. Now, let us consider your crystal itself. Your crystal is going to be made up of n, capital N number of such primitive cells. It is made up of n number of such primitive cells. So if I talk about the reflection of the X-ray from the entire crystal, then what I need to do is I will say that it is equal to n into the structure factor, where capital N is the number of such primitive cells present in your total crystal. Okay, and from optics, you also know that amplitude and intensity are related. You know that intensity is proportional to the square of the amplitude. Intensity is proportional to square of amplitude. Please remember, amplitude of a wave you cannot see. You cannot see the amplitude of a wave. But intensity is brightness. That is something that you can see. Like for example, you saw those peaks. Those peaks are the intensity of the reflected X-rays. Okay, those peaks actually represent the height of the peak represents the intensity. Largest peak means largest is the intensity. Okay, so we will take the structure factor, square it, and that gives you the intensity of the wave, of the reflected wave. Okay. Now what we'll do is, this is something general that we have seen. Now what we'll do is, we'll apply it to different types of structures, different types of lattices. And we will first talk only about monoatomic. Monoatomic means in the given structure, all atoms are the same. Then it is monoatomic. So let's first of all start with BCC. BCC means body centered cubic lattice. Okay. So for that, you need to know what is the primitive cell of BCC. You know how a BCC will look. There will be one lattice point at the center, at the body center, and then 8 at the corners. Okay. Now, a BCC's primitive cell is simple cubic. You can treat a BCC containing identical atoms as simple cubic. You can treat it as simple cubic. And in that simple cubic, what is present in each lattice you have to see. You can take these two fellows and pretend that they belong to this lattice point. Similarly, if you take the next cells also, each time you can take one here and another in the next cell. Okay, so you can say that your basis is 2 atoms. Your basis is going to contain 2 atoms. And inside this cell, where are these 2 located? This is the origin, so it is located at 0, 0, 0. Okay, and where is it located? Body centered. Body centered means you come half along A, half along B, half along C. Then you go to the center of the cube. Therefore, you can say that the body center is actually half, half, half. This will be the coordinates. The coordinates of the 2 atoms are 0, 0, 0. I should do one thing. I should not put this bracket, because if I put this bracket, you will think it's HK. Okay, the coordinates will be 0, 0, 0 and half, half, half. I hope you understood how this has come. Okay, now what you do is, let's call this as R1 vector and let's call this as R2. So these are the positions. And now you have to put it into the structure factor formula. What is the structure factor formula? Sg equal to F into summation exponential Ig dot Rj. But here there are only 2 J's, R1, R2. So I have to substitute this R. But before I substitute R, I should know what is, okay, first of all, let us substitute R. When you substitute R, you will find that there are 2 terms. When I put a summation here, J equal to 1, J equal to 2. So the first term will be F into exponential 0. Exponential 0 because R1 equal to 0. Plus F into exponential IG into this half, half, half. Okay. Now, how do I write this half, half, half? Half, half, half can be vectorially written as, because it is half. And if the cell size is A, it is A by 2 into X cap plus Y cap plus Z cap. Okay, half, half, half means A by 2. A by 2 I'm writing because A is the size of the cell. You're going halfway along X, halfway along Y, halfway along Z to reach that point, half, half, half. Okay, so you're getting two parts like this. Exponential of 0 is 1. So you get F plus F into exponential IG, then half, half, half. Okay. So next what you do is, what is this G? We have to know G. To know G, I will take you to reciprocal lattice. In reciprocal lattice, you have studied that GHKL is H A star plus K B star plus L C star. Then A star, B star and C star were the reciprocal lattices. Okay. And we have seen that we are now assuming that this is simple cubic lattice. Your BCC can be treated as a simple cubic lattice. And you know that for a simple cubic lattice, you know how G will be. G will be 2 pi by A into M1x plus M2y plus M3z. This you go back and see. This is for GHKL. Those of you who attended class the other day will know that we have written G100 and we wrote it as 2 pi by A x cap. The other day, people who were in the lab, in the class will realize that I wrote this. Who was there in the class? Abhishek, were you there? I hope I'm getting the name right. Abhinav, sorry. Abhinav, do you remember this? G10, for example, G100 could be written as 2 pi by A x cap for simple cubic. Okay, so just extend this, you will be able to see how I got this equation. Okay, so now make that substitution. Make this substitution for G into the above equation. So you get your structure factor as F into 1 plus exponential I pi M1 plus M2 plus M3. Why am I getting this? I'm getting it because I'm just substituting it here. Okay? Or if you want, I'll just do this and show. You're going to get I into G is 2 pi by A M1 x cap plus M2 y cap plus M3 z cap dot. You already have your R1. R1 is A by 2 into x cap plus y cap plus z cap. So do the dot product. What will you get? A and A will get cancelled out. 2 and 2 will get cancelled out. You get I pi into M1 plus M2 plus M3. That's how you got this. Okay. And F is common. Take it out. So you get 1 plus exponential I pi M1 plus M2 plus M3. Okay. Now you know that exponential of I pi M1 plus M2 or exponential I pi x can be written as minus 1 to the power of x. So that's what we are doing here. So you write it as minus 1 to the power of M1 plus M2 plus M3. Okay. Now comes the important part. Okay. Now comes the important part. Now look at this. Take this equation and see when your structure factor Sg will be a maximum. When will it be 0? Let us see that. Okay, now look at this. If M1 plus M2 plus M3 is an odd number, what is minus 1 to the power of an odd number? What is minus 1 to the power of an odd number? Minus 1. Oh, you have come to class. Minus 1. So look at this. 1 plus minus 1. So you get 0. You get 0 whenever the sum of m1 plus m2 plus m3 is an odd integer. Is an odd integer. And what happens if it is an even integer? If it's an even integer, minus 1 to the power of an even number is plus 1. Therefore, you get the structure factor as 2f. Okay. Now, I need to interpret these equations a bit. Let me just try doing that. What this means, let us see. Yeah. You see here, in the last class, I mentioned that GHKL is H A star plus K B star plus L C star, where A star, B star, C star are the reciprocal primitive lattice vectors. Okay. And we have seen that for a cubic system, A star, B star, C star, all the three of them are going to be equal, but they are mutually perpendicular to each other, we have seen. And their length is going to be 2 pi by A. This is what we have seen. Okay. Now just make a comparison between this and this part of the equation. When you make a comparison, what is it you're going to see? You're going to understand that, let me write, A star without a vector symbol, A star equal to B star equal to C star equal to 2 pi by A. Equal to 2 pi by A. So, what would this mean if you make a comparison between these two equations, left side and right side? What would this mean? Let me also write one more step. Let me also write one more step. Your A star equal to 2 pi by A along x cap, B star equal to 2 pi by B, 2 pi by A along y cap, your C star equal to 2 pi by A along Z cap. This is for cubic. Okay. Now, from all this, you can come to a conclusion. What is the conclusion you can come to? You can conclude that this M1, M2, M3 are simply your H, K, and L. Your M1, M2, and M3 are simply your HKL. What is this HKL? HKL is the indexing parameter for the different planes we have done, you saw. So it is that same HKL. That is the reason why the other day I wrote G100 as 2 pi by A x cap, which is A star. Similarly, we wrote G101 as 2 pi by A y cap, which was your B star. Okay, similarly, G1, I'm sorry, 001, I'm sorry. Here I made a mistake. G010. Here I'm talking of cubic, okay? Cubic. If it's not cubic, then I would have written 2 pi by A, 2 pi by B, 2 pi by C. Okay, so in general, GHKL by this logic, you will get your GHKL as HA star plus KB star plus LC star, where HKL are the indexing. They are the directions of the plane. Okay. So this M1, M2, M3 are also the same as your HKL. It's the same. It's HKL only. So now what do you conclude from all this? You can conclude that for a BCC lattice, Bragg's peak, you will not see for H plus K plus L being odd. H plus K plus L being odd. That means you will not see 1, 0, 0. You won't see 1, 1, 1. You won't see 1, 2, 0. Like this you can go on. Why will you not see this? Because 1 plus 0 plus 0 is odd. 1 plus 1 plus 1 is odd. 1 plus 2 plus 0 is odd. So you won't see these reflections. So what are the reflections you will see? You will see reflections corresponding to M1 plus M2 plus M3 or H plus K plus L equal to even. So look at this. 110 even. 101 even. 011 even. 200 even. So whenever it is even, those reflections you will find. This is for BCC. Now let me just go back to the previous picture. Now look at this picture. What did I show you? What did I tell you was this X-ray diffraction pattern? I said this is the X-ray diffraction for a BCC metal. A BCC metal is going to have a unit structure, a primitive lattice, which is simple cubic, and it is going to, you can take the basis as two atoms sitting at 000 and half, half, half. And look at the peaks here. See the peaks? 110, 200, 211. They are all corresponding to H plus K plus L or M1 plus M2 plus M3 corresponding to even. Are you able to see that, guys?
Yes, ma'am.
So now we will do the same. So at the end of it, you will know for an examination what are the things that you should know and remember. You should know how to write the, you should know the relationship between A, B, C, A star, B star, C star. Similarly, for a cubic crystal, how do you write your, uh, what is a primitive lattice structure? Where are the atoms located? Similarly, how do you write the G for a simple cubic? At least for a simple cubic, you should know how to write your G vector. Okay, now let us see the structure for a structure factor for a monoatomic FCC lattice. You know what's an FCC lattice? So there are 4 and 1, 4, 5, 6. So there are 6 faces. At the center of each of these 6 faces, there is going to be an atom or there is a lattice point, and then there are atoms at the 8 corners also. So this is your FCC lattice. Okay, now how can you talk about a primitive lattice for FCC? Because FCC is going to have more number of atoms than one. So how do you write a primitive lattice for FCC? For FCC also, you can write a simple cubic as the primitive lattice. A simple cubic as the primitive lattice. So how do you do that? Take one of the corners and take the 3 nearest face centers. Take the 3 nearest face centers. One on the face in front, one on the left face, and then one on the uh, bottom, one on the bottom. So you have to consider your basis as this cluster of 4 atoms. You have to consider your basis as this cluster of 4 atoms. So if you consider your basis as this cluster of 4 atoms, then you can treat this lattice structure as simple cubic. Okay, so if you keep on placing these 4 atoms and proceeding in space, you will get your FCC. But then the primitive lattice is simple cubic only. Simple cubic with basis consisting of 4 atoms. And where are the 4 atoms located? They are, one is located at the corner, let's call that as 000. Then another is located at one of the nearest face. Nearest to face, center of a face. Center of a face means what? It is on a plane, therefore you can take one of the coordinates as 0, the others will be half and half. Okay, similarly, if you take a face like this, the coordinates are going to be half, half, I'm sorry, half, 0, half. Similarly, for a third phase, it will be 0, half, half. Are you understanding how we got these 4 positions? So one of the corners is going to be 0, 0, 0. I should not put a bracket there. Let me not put a bracket there. Okay. So I hope you understood how the atomic positions are coming. So take one corner atom and then 3 nearest face centered. If you take this as a basis, then your crystal structure is simple cubic. Okay. So now you can write the positions of these. You can write the position vectors of these as 0. And then half 0 will be a by 2 x cap y cap. Why a by 2? Because the size of the cell is a. So a by 2 x cap plus y cap. Similarly, a by 2 z cap plus x cap. Similarly, a by 2 y cap plus z cap. Then you just have to do what you did previously only. You have to write Sg is equal to structure factor is equal to summation f into exponential I g dot rj. Okay. So where rj will be r0, I'm sorry, r1, r2, r3 and r4. Make substitutions. But again, if you want to complete this problem, you need to know what is G for simple cubic. Please remember what is G for simple cubic. For simple cubic, G is 2 pi by A. Previously also we wrote that. 2 pi by A, M1 x cap plus M2 y cap plus M3 z cap, where this M1, M2, M3 are, what are they? They are simply your H, K and L. Okay. So make a substitution, do a dot product. When you do a dot product, you are going to get only 2 terms every time. And the first one is just going to be 1 because you're going to get exponential 0 because R1 is 0. And F is common, take it out of the bracket. So you get F into 1 plus minus 1 to the power of M1 plus M2 minus 1 to the power of M3 plus M1 plus minus 1 to the power of M2 plus M3. Definitely expect questions from this. Okay, next. You have to now see what are the conditions when Sg, structure factor, will be 0. What are the conditions when they will be non-zero? Okay, now you see here. Sg will be equal to 4F. Sg will be equal to 4F whenever M1, M2, M3 are all even or all odd. You're going to only add 2 at a time. You're only going to add 2 at a time. You see here M1 plus M2 or M3 plus M1 or M2 plus M3. So if all the 3 of them are odd also, each time you're summing, you're going to get an even. Or if all of them are going to be even also, when you add up, you're going to get even only. Because you are adding only 2 at a time. I hope you're getting that logic. So here, this is going to be different from BCC. In BCC, what did you say? What did you get? The sum should be equal to even if you should get non-zero. Here, either all of them should be even or all of them should be odd. No mixing. Let us say, for example, if M1 is 0 and M2 is 1. M1 is 0 and M2 is 1. Then you will get exponential I pi as minus 1. Okay. So this is what it is. If all of them are even or all of them are odd, then each of these factors will contribute and you will get 4F. There were 4 terms. What does this mean? This means that you will see reflections like 111, 200, 220. But of course, when I'm writing 200, I am missing out on 020, 002. They're all equivalent. That's why I'm not writing that. Okay. So these reflections will be seen because you're seeing that all of them are either even or all of them are either odd. So what are the reflections that will not be there? Whenever there is a mix of M1, M2, M3 being a combination of odd and even, that minus 1 to the power of odd you will get, which will be minus 1. Therefore, the sum will simply become 0. You're going to get, when there is a combination of odd and even, there were 4 terms, okay? 2 will become plus 1, 2 will become minus 1. Therefore, the sum will become 0. So what does this mean? This means that you will not see reflections like 100. It's a mix of odd and even. You won't see 110. That's a mix of odd and even. You will not see 1 to 1, mix of odd and even. Okay, so this is how writing the structure factor will help you identify what types of reflections will be there in your X-ray pattern. So even by indexing your lines, you will be able to predict what would be the structure. Now let us go to the simplest thing. This is not there in your book, but I thought I'll just put it there. What will be the structure factor for a simple cubic lattice? What is the meaning of simple cubic lattice? Your simple cubic lattice means there is only the primitive cell is also simple cubic. Primitive cell is also simple cubic. And where is the atom located? There is only one atom per basis. There is only one atom per basis and it is located at the origin, 0, 0, 0. That means your structure factor is now going to have only one term, f into exponential ig dot 0. You know exponential of 0 is 1. Okay, therefore, this will be equal to not 1, it will be equal to f. It will be equal to f. F into 1. F into 1, f. So that means there is going to be no dependence of H, K, L or M1, M2, M3 on the scattering factor. From any of the planes, you can have scattering and the scattered ray will be, there will be a constructive interference corresponding to any combination of H, K, L. So that means there is no missing peak. There will be no missing peak. Let us quickly try to write the reflections. How you write the reflection starting from the lowest, let us see. HKL, the simplest will be 1, 0, 0 plane or 0, 1, 0, 0, 0, 1 and just clubbing them all and writing 1, 0, 0. Then let us go to the next possible families, 1, 1, 0. 1, 1, 0 also includes 1, 0, 1, 0, 1, 1. I'm writing them as just one family. Similarly, you can go to 1, 1, 1, 2, 0, 0, 2, 1, 0, 2, 1, 1, 2, 2, 0. Then you can go to 3, 0, 0. I hope you're getting some idea of how you will write your HKL. Please remember, HKL can take values 0, 1, 2 integer values, including 0, no negative. HKL cannot be negative. So how the simplest to complex you will go is what we have shown here. Like for example, this may be 1, 0, 0. This may be 1, 0, 0. What will be 1, 1, 0? 1, 1, 0 will be, let me draw another picture. 1, 1, 0 will be this plane. Okay. Similarly, what will be 1, 1, 1? 1, 1, 1 will be a plane. This will be the plane. Okay. Similarly, you can talk of 2, 0, 0. 2, 0, 0 will be a plane which is parallel to 1, 0, 0 but cutting at half. So this is your 2, 0, 0. This is your 1, 0, 0. Please, you must be very good at locating the atom, the reciprocal lattice, HKL. If you're able to do this only, you will be able to get any marks in the examination. Okay. Now, let me quickly just try to, this diamond, I don't want to, it is there. I've just written it for the sake of writing. You just leave it. If you understand the other three, that itself is a big deal for your age and maturity. Now, till now we talked about monoatomic. Now let us go to polyatomic crystal. What is the meaning of polyatomic? Anyone? What is the meaning of polyatomic?
More than one.
More than one type of atom. Like for example, NaCl, cesium chloride, copper, zinc. These are all alloys and they are all having more than one type of atom. So let us take for our example, copper, zinc. An alloy of copper and zinc. And if you see the structure, it is going to have the cesium chloride structure. It will have cesium chloride structure. What is cesium chloride structure? We have seen that in the previous chapter. Cesium chloride structure is simple cubic, but the basis is going to have two atoms, one cesium I mean, one copper and one zinc in our example, or one cesium and one chlorine. If there are two elements, means the basis is going to have two atoms, one of each type. One of each type. And how will the cesium chloride structure look? Actually, you should have studied all this and told me you're not studying anything at home. That is very clear. So one will be sitting at the body center and the other type of atom will be sitting at this corner. So this will be 0, 0, 0 and the other will be half, half, half. Okay. So now you must remember that if you repeat this structure, this simple cubic structure with two bases, one being copper and the other being zinc, if you please translate this in 3 dimensions, then what you get is going to be your cesium chloride structure. So now you have to remember why this is different from the previous discussion. In the previous discussion, this F is called the atomic factor. This F is called the atomic factor. The atomic factor, I told you, depends on what is the atom. Here, because there are two different atoms, the atomic factor will not be the same for both of them. Atomic factor for copper you have to write, atomic factor for zinc you have to write. Okay, and you also need to at the same time know this G for simple cubic. That's a foregone conclusion. You need to know it. And then half, 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 you know how to write R1. R1, you will write it as A by 2, X cap plus Y cap plus Z cap. That's also fine. And here it's going to be exponential 0 because your R1 was equal to 0. Okay. Or now when you simplify and write, you will not be able to write one common F and take it out of the bracket. You have to write F copper plus F zinc into this. F zinc into this. Okay. So this is how you write the structure factor. Okay, this is how you write the structure factor. Please remember, for a perfect crystal, what happens is FCU and F, the atomic factors will never be the same for two different elements. Okay, that is a foregone conclusion. In a real crystal, in a real material, what happens is a real material will be polycrystalline. You studied this in SPM, it will be polycrystalline. You will have the crystal made up of different crystallites of different orientations. So as a result, what happens is, if you keep putting points in space and going, okay, there is a great probability that your 0, 0, 0, here when I'm talking about this crystal, if I'm talking about this crystal, within this crystal, maybe all the 0 zeros of each primitive cell are occupied by copper. But when you come here, the 0, 0 zeros may be occupied by zinc. Okay, so the probability that a copper is at 0, 0, 0 and zinc at half, half, half is equal to the probability that a zinc is at 0 and copper is at half, half, half. That is simply because of the disordered nature of the material. But there are different crystallites of different orientation. So that is the case, you can simply take an average of the atomic factor of copper and the atomic factor of zinc. You take the average, okay, and write this as average atomic factor. Okay, so you can use the concept of average atomic factor and then take it as common, take it out of the bracket and then write your equation. Okay, and this is actually the average structure factor and the small f is the average atomic factor. Now, of course, you can see when this is going to be a maxima, when this is going to be a minima. You will be able to see that the structure factor will be 0 when M1 plus M2 plus M3 is odd. M1 plus M2 plus M3 is odd. If it is odd, you will get minus 1 to the power of odd, which is minus. So plus 1 minus 1 will be 0. So again, for these kind of materials also, you will not see the peaks corresponding to M1 plus M2 plus M3 being odd. Okay, this you don't bother, just leave it. In the next class, I'll just complete this chapter. Okay, please, whatever I'm speaking will be, first of all, crystallography is a tough subject. It requires a lot of imagination. Next thing is, you people are not studying then and there. I'm able to see that lacuna in the class. It has become a monologue. I am only talking. Because if I ask you, can you answer this? Nobody's answering. Okay, don't bother about diamond structure. Just leave it. It's okay. You don't need to study this. Don't bother. I wrote it, but then I am thinking that you guys will find it very tough to take this diamond structure. So let's not bother with diamond structure. Let's do the other thing. To the diamond structure, you know how the atomic spacing will be. Okay, it's actually going to be two FCCs at quarter body diagonal with respect to each other. Slightly tough for you to understand. Let's just leave that. Other things, the other basic things, if you're able to write in an examination, that itself is a big thing for me. Any doubts on the examination, guys? I hope there are no doubts. If you have any doubts, please, we have that WhatsApp group. Please go there and ask questions.